Okay, so I think it's a good time to start. I'm not going to be seeing the meeting chat, but please, Kyle, let me know if anyone sends something there. You guys feel free to interrupt me whenever you want. And please do, in fact. I didn't prepare that much stuff, so I'm not going to be able to fill 2 hours on most of the days unless you ask me things. So that is something really important. And today in particular, I'm going to have to leave early because I have a poster session that I'm participating on another event, and it starts in roughly 1 hour. So today is going to be a shorter section, but still, please ask me things. We have enough time for many questions in the course. I didn't prepare that much stuff, so, and I think it's going to be all right. So feel free to interrupt me. Now, the way I always like to start talking about quantum field theory and curved spacetime is with something that I like to call syllabic questions, which are questions that a toddler could ask, but that are really difficult to answer. So, for example, how did the universe begin? Why does time move forward? What are things made of? What is time? Or why do things fall? In this course, we're going to focus mostly on why do things fall and a little bit less on what things are made of. And it's interesting to wonder about these questions because ever since the ancient Greeks, we already have some answers to them, but they are not really satisfactory. So, for example, in ancient Greece, things were made of 5 elements. These were the usual 4 elements: water, earth, air, and fire. And the fifth element would be ether, which composes things above the moon and the moon itself. And they fall due to their natural motion. They just have the tendency to move back, to move down or upwards, depending on which one is which. So fire tends to go up, air tends to go up, earth tends to go down, water tends to go down, and ether moves in circles. So hence, you explain the gravitational effects in terms of the natural motion of these 5 elements. Nowadays, we have a different answer for each of these questions. For what things are made of, we say that they're made of the field of the Standard Model, which is a quantum field theory describing everything we know of. And things fall due to general relativity, which describes that matter curves spacetime and gravity is simply the motion on this curved spacetime. However, there's something interesting in this. When you pick the SM, this is a quantum theory, so it uses the laws of quantum mechanics, and in particular, it gives you operators. If you ask what is the energy somewhere, it's going to give you an operator uh, h hat, which is an operator and not a function, not a real number. It is the Hamiltonian of the system. As for GR, it is based around the Einstein field equations, where you have GAB equals h pi TAB, and where you have this is the curvature of spacetime. It tells matter how to move, and this is the presence of matter, which tells spacetime how to curve. What is interesting here is that if you were to use quantum matter in GR, you would run into the issue of having an operator equal a real number, which is not really possible. Hence, GR itself does not uh, talk the language of quantum mechanics. It does not know of quantum mechanics. It is a classical theory. And in order to be able to describe how the things that make everything up fall, we need to somehow improve on GR. The simplest way to do it is to consider what we call quantum field theory in curved spacetime. I like to draw it as this pseudo equation in which we add an expectation value of the stress energy tensor in here, and now we let spacetime tell classical matter how to move, classical matter tells spacetime how to curve, and let the geometry of spacetime tell quantum fields how to move, but we do not draw the other arrow. That would be semi-classical gravity, which is another thing that I'm not going to discuss in this course. And it is way more complicated. So what we have here, which we call QFTCS, is this interplay in which we let classical matter and space-time tell each other how they should evolve, and we evolve light fields. By light, I do not mean light in the sense of luminous, but in the sense of not heavy. We let light fields evolve in this curved space-time. In this way, we are not obtaining a fundamental theory. We are not obtaining a final theory of how the universe should behave, but instead, we are having a very simple way that uses the basics of what is quantum field theory, which is one of our best tested theories, and what is general relativity, which is also one of our best tested theories, to interplay together and hence tells us how exactly quantum effects react to the presence of gravity. So far, so good. I'm gonna let you
Sorry, can I
few
ask
minutes.
a question? Very nice question.
Yes.
The last arrow that you drew, so GAB feeding back to the expectation value of TAB.
So,
That
sorry,
expectation value is
could you say a little bit more slowly, please?
yeah, sorry. Yeah. So the last arrow that you draw, that is like the GAB feeding back to the expectation value of the sensor, right?
Yes.
So that is calculated in some state. So very nice if we try to compute what that state would be. Won't you find that it non-linearly depends on the metric? The state in which the expectation value is calculated. I mean, is it going against the linearity of the quantum theory in some sense?
I think I'm not really sure the state is calculated because I'm not really
So what state are you using to
knowledgeable.
calculate the expectation values? I mean, the expectation value here is in some with respect to some state.
Yes, you have to take the expectation value with respect to some state, which is some state omega, for example. But I'm not really sure
So
whether
won't
you
that depend
compute the
non-linearly
state.
on the metric?
I'm not sure whether you compute this state. I think usually people take the state for granted, and then what they usually do, to the best of my knowledge, is you pick the state, you solve this, you
Right.
pick an admissible state in this geometry.
Correct.
Now you add this contribution here.
Uh-huh.
You let it back react. This is going to update
Yes.
something. Now you have a new state, omega prime. You're going
Yes.
to feedback, and then you keep doing this, and you have a
So
perturbative
isn't this
description.
feedback mechanism non-linear? Like, I mean, is it? I don't see it to be linear in some sense with respect to the metric.
I don't see how it needs to be linear with respect to the metric.
So you calculate for the wave functional, right? And the wave functional has to be containing the field as well, the metric field.
Yes, it is going to depend on the metric somehow.
Yeah.
And I don't
So I
see a
would have
reason for
expected
it
it
to
to
depend
be.
linearly.
Maybe we can discuss this later. Yeah. Anyway,
Yes,
thanks.
perfect. Any other
Nick,
questions?
AC asks, aren't we just using what Einstein had used as matter?
Yes, we are using what Einstein had used as matter, which is classical matter, and we are describing as test fields how we move on this Einsteinian spacetime. Does this make sense?
The person said yes.
Okay,
May I say something?
sure.
Well, just to add to what Krishna was saying, I think that quantum theory in curved spacetime only works on Hadamard states, right? No other states are used?
Sometimes you are interested in a non-Hadamard state. I'm going to get there. But it
Okay.
depends on many things. So it is not a Hadamard state on a full space time, but it is Hadamard on a region, and you're interested in this region, then you might use some state that is not Hadamard in the whole space time. But mostly we are concerned with Hadamard states, which are renormalizable states.
Okay, thank you.
I'm going to comment on that on the next lecture. Okay, anything else?
No, thank you. Well, at least for me.
Okay, I'm going to proceed. So one of the things we have to ask ourselves when we're doing this is which spacetimes we're going to consider. Because if we're going to pick any spacetime, we run into an issue. Einstein said the subtotal is the Lord, but malicious is not. On the other hand, generals are the Einstein equations, but malicious too they are. So if we're going to pick any spacetime with general relativity, that is way too vague, way too wide. Because, for example, I might pick Minkowski spacetime and just identify sometime t equals big T with t equals 0, and hence have trajectories that move like this in the spacetime. And then you can have closed causal curves, so I can have a curve that starts here and then it starts again on the very place it was, which means you can go back in time. That is not really interesting for us, because if we want to quantize a theory, we should expect it to at least be solvable classically. So I should be able to obtain a result for the theory classically, and this is not possible in this sort of spacetimes. If I give you initial data on some surface and try to evolve it, this might not be possible if the spacetime is too wild. So you want to pick a spacetime that is well behaved in the sense. To do so, we will require the spacetime to have a Cauchy surface. This is a surface that is topologically closed, which is a technical requirement. You don't need, if you do not understand what topological means or closed means, there's topologically, I think it has two L's. Closed. Every time-like curve intersects it once and only once. In every light-like curve intersects it. So an example in Minkowski spacetime would be you have here Minkowski spacetime, and a Cauchy surface is just the surface t equals 0 or t equals a constant for whichever time you choose for an inertial observer. This is going to be a Cauchy surface. On a more complicated example, you can pick a black hole spacetime, which we can draw like this. This dashed line to singularities. You have here the black hole region, you have here a white hole region, you have here a universe, and you have here a parallel universe. And an example of a Cauchy surface would be, for example, something like this, which goes from spatial infinity in here to spatial infinity in here. An example of a spacetime that does not admit a Cauchy surface is ADS spacetime. So we're not going to be considering anti-de Sitter spacetime. We are instead going to consider, for example, de Sitter spacetime, which do admit a Cauchy surface. Spacetimes that admit a Cauchy surface are called globally hyperbolic. And the interest that we have in them is that we can solve initial value problems. So for example, I can pick the Klein-Gordon equation, which in curved spacetime reads like this. Yes, I'm using the minus plus 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 metric always. And I can solve it, or I can even add a source in here. And I can solve it given initial data values, initial data of some Cauchy surface, and I can obtain a solution to roll the spacetime. Hence, a globally hyperbolic spacetime can be thought of as a spacetime in which the classical theory is well defined. So far, so good.
So can we not make sense of quantum field theory on an ADS spacetime?
I'm not really sure how people deal with ADS spacetime, but there are works on non-globally hyperbolic quantum field theory. So there are people who interest themselves in non-globally hyperbolic spacetimes, and I believe there are results on how you can deal with QFC in these sorts of spacetimes, but I'm not really familiar with it. In the case of ADS, something you can do too is this is the Penrose's diagram for ADS, and you can pick the Cauchy surface in here. It is going to make this is sort of a Cauchy surface, but it's going to determine only something like this region, so a diamond. Within this diamond, you can do quantum field theory in curved spacetime because it behaves just like as a globally hyperbolic spacetime.
Right. So the problem is that if classically we cannot formulate the initial value problem, quantum mechanically we should not expect the problem to be well defined. Is that the right thing to say?
Yes, in quantum mechanically, you are going to have at least some issues with defining the Hilbert space, with defining, as we showed you in algebra observables. It gets a little bit more complicated because you need some good definitions in order to define everything up.
Okay, thanks.
You're welcome. We're going to use the classical theory to define the quantum theory, and hence we need the classical theory to be well defined. I'm not really sure how people deal with ADS, but you probably need to make some changes to what I'm going to do.
Nick, there's another question. Is the covariant derivative in the Klein-Gordon equation corresponding to the Christoffel connection or some other type of non-symmetric connection?
Christoffel. This is the connection generated by the metric. Does it make sense? I'm considering just spacetime which is defined by a metric, so it defines everything I'm going to write up.
It's all right.
Okay. Yeah, it satisfies this equation. Yes, for those of you who might not be familiar with general relativity, this derivative is a version of a usual derivative, but it keeps whatever I derive as a tensor. So you have these issues in curved spacetime. You need to be careful with the derivatives you take so that your objects are still tensorial. If you just take usual derivatives, you're going to lose the tensor aspect. So okay, we have here a number of spacetime. And hence, in order to introduce to the first approach to quantum field theory in curved spacetime that I'm going to pick, which is the algebraic approach, we're going to start by wondering, what is a quantum theory? To describe this, I like to start by wondering what is a theory at all. And what I'm going to do is the following. I'm going to assume that when I perform some experiments, so I have some box in here where I have my experiment, there is some apparatus A in here. I'm going to prepare the state or the system in some manner omega. I'm going to let the state, I should not say state at this time. I'm going to let the object I'm investigating interact with this apparatus, and then I'm going to have an outcome, which might be a probability. So the probability of getting the result Q, when I prepare the system in a manner omega and use the apparatus A, is P of Q omega A. So this is prob of Q given omega and A. We can assume that any physical problem is going to give us some sort of probability distribution like this. It might not give us always the same value, it might give different values, but we can always get some probability distribution. Otherwise, it's hard to even think about how we would do physics. So we pick this probability of Q, and there are some things that we can do now. For example, suppose I have two different apparatuses, A and A prime, such that whenever I prepare the state, the system in a manner omega, they lead to the same results and the same probabilities. So they have this property that P of Q omega A equals to P of Q omega A prime. For example, I can just measure the mass of something in two different scales and see that both scales give the same result. In this case, there's no real need for us to separate what is A and what is A prime. Instead, we can consider A as being A prime. They are equivalent. And hence, we call this equivalence set or this equivalence class, which are all observables that are equivalent to A, as being, which are all apparatuses under preparation that are equivalent to A, as being unobservable. So unobservable is an equivalence class of preparations of apparatuses. Yes. We're going to denote the class, the set of all observables by fancy A. We can similarly define a state, which is when I pick two different preparations of something, or two different things and prepare them in the same way, or two different things and I prepare them in different ways, and I pass them through the same apparatus or through the same observable, and I find that PQ of omega A is always equal to PQ of omega prime A for any observable and for any Q. In this case, there is no need for me to distinguish between omega in omega prime. So I'm going to call them the same thing, and I'm going to say that they correspond to the same state. So that is what I mean by an observable and a state of a system. So far, so good.
Sorry, the observable was the equivalence class of the apparatus. And what does the state correspond to? Equivalence class of?
Equivalence class of is an equivalence class of preparations of a system. So it is an equivalence class of the way you prepare the system.
In the sense of taking probabilities, do you assume that preparing the system gives you full knowledge of the a priori probability of a state?
Yes, I am assuming it. So you could also say that the experimentalists or the laboratory also interfere with the probabilities, but I'm simplifying and assuming they don't. So I'm assuming that preparing the state, the system, and preparing the apparatus gives me complete information of the a priori of the experiment.
All right, got it. Thanks.
You could make it more complicated by trying to deal with who is performing the experiment, and then it depends a bit on your interpretation of quantum mechanics, or how much the environment interferes. But I'm assuming everything is encoded in these two guys. This is the description given by Araki in his mathematical theory. Of quantum fields. So we can start to play around with these definitions a bit. For example, the outcomes Q can be anything. I could use, for example, in an ammeter, a scale which has this marks here and indicate how much current I'm measuring. So perhaps this is 10 milliamps, this is 20 milliamps, and so on. I could use color instead of this if I prefer. So I would have red over here. I'd have orange over here. I'd have yellow over here. And hence 10 milliamps would correspond to some yellowish orange. And so on and so forth. I can choose to label the results in whichever way I want. But it is usual and convenient to assume that Q is always a real number. So that is what we're going to do. We assume that Q is a real number, not because we need to, but because it is convenient. And hence it allows us to have a standard we use for any experiment.
I have a question.
Yes.
Why not be a natural number? Why does it have to be a real number?
For convenience, it could be a natural number as well, but when you see, for example, an ammeter, it is sort of continuous. So it is difficult for me to use a natural number to describe what is in between what is pointing here, for example, because I would have 1 over here, 2 over here, 3 over here, and what is between 1 and 2, so it gets difficult.
But isn't it more, I guess, usual in quantum mechanics to have discrete things?
Yes, you might have discrete results within quantum mechanics. But this description we are performing so far, it is quite general for both classical and quantum mechanics. So these probabilities are not necessarily quantum. They might also be classical.
Okay, thank you.
Does it make sense?
Yep.
In quantum mechanics, you would have something like the probability of Q is usually 0 for most Q. You have just a few probabilities that doesn't vanish.
Hi, can you repeat the reason for why it has to be, I mean, why it is conveniently taken to be real numbers and it can be complex number?
Why it is convenient to be a real
There
number.
was, yeah, and not has to be a real number.
And a real number and not a natural number, you mean?
Yeah.
Yeah,
I
because
mean,
for
you said
example,
it's convenient to, yeah, sorry, go on.
because if I label this with natural numbers, for example, I'm going to run into an issue where the needle is pointing here. Not really on 2, not really on 3, but something in between. So it
Oh, no,
seems to me,
my question is different. I mean, you said it is convenient for us to take it to be real numbers,
yes,
and it's you seem to imply that it's not a necessity for measurements to be a real number. The outcome of a measurement or whatever Q has to be a real number, right? I mean,
yes.
said it's
But it could,
convenient for us to take.
yes, an inconvenient choice, for example, would be to label everything with ones. I just pick my A meter and I stick some tape in here, which has a 1 in the front. So whichever is the result, I'm going to say it is 1, wherever the needle is pointing. Can I do that? Yes. Is it useful? Not really.
Okay. Yeah. Okay.
So it tends to be convenient to pick real numbers within some range or something like that. Which is, of course, what we usually do when we're taking measurements in the lab. But we could, in principle, use ones in everything. We could use a color scheme. It is just not really convenient, but it is possible in principle. So if there aren't any more questions. Okay. Using this notion that the results are always real numbers, we can define functions of an observable. I'm going to say that a function of A is the observable that yields f of q whenever A would yield q. So I'm just mapping the results. It's just like I'm picking the A meter and it had some values in here. It had 10 amps, for example, it had 20 amps. And I'm just applying this function, and instead I'm going to read f of 10, f of 20. I could do that with a sticker, for example. And hence I change the scale. In this way I can define new observables. There are functions of this observable A. For example, I can define A to the n, which yields P of n, Q to the n, whenever A yields Q. This is interesting, for example, because I can now start doing the following. I'm going to define that the state omega acting on A equals to the expectation value of Q with respect to this probability. Using this construction, I get an omega of a to the n is equal to q to the n p of q omega a dq. And hence I can use this guy to find the moments of the distribution P. Using these moments, I can omega a for all a lets me know P of q omega a for all q and for all a. Alternatively, you can also define a function chi r of q that is 1 if q is r and 0 otherwise, and see the P of r omega a equals to omega of chi r of a. In both cases, the point is I can describe a state either in terms of these probabilities or in terms of these expectation values. So knowing the expectation values is enough for me to know the state completely. Okay. This allows us to start introducing. Hey.
Now I have a question. This states and the observables and so on, they live in different spaces, right?
Yes, the states and the observables live in different spaces.
So the observables, they don't live in like coordinate spaces. They live like, because I'm thinking in terms of GR, because that's what I'm most familiar with. So what I'm thinking is that these observables live in the manifold itself, or I'm
No.
choosing in this. Oh, okay.
No. An observable, for example, is energy. So can I measure the energy of something? And hence I have some experiment in here, some box, in which I'm going to pass a particle, and it's going to spit me the energy is E.
Oh, okay.
Once I measure it. So the energy is unobservable.
Okay, makes sense.
All right. So we can use the fact that we can use expectation values to describe these states to introduce some more structure on the space of observables A. For example, I can define addition in A.
Sorry, are you assuming a Hilbert space to begin with? Where is omega coming from?
Omega is a state.
Right, so this is coming from a Hilbert space, right?
Not necessarily. This is going to be wider than a
what is
Hilbert
the meaning
space.
of state here?
State is this I define up here. It is an equivalence class of preparations of a system. Later, we will be able to capture a Hilbert space.
I see. So far you have not assumed any Hilbert space, but you have a notion of defining like, I mean, usually in quantum mechanics, the complete description of a system is the quantum mechanical state of the system, right? And it is member of some Hilbert space. So I'm not able to relate what omega is like. Where is it coming from? Like
omega
mathematically, where does it belong? Like
it belongs actually. It is a functional, as I'm going to show, on this algebra of observables A. So it is something that we think of here as a state as something that eats an observable and spits the expectation value. This can be,
And
this is enough to describe any quantum state, because you can always write any matrix element in terms of expectation values. It is a little bit complicated. You have to use something like psi plus psi, pi plus psi, blah, blah, blah. But you can always write this in terms of expectation values. This
okay,
is
so omega is a collection of functionals on the A that you are defining, this curly A that you will define.
yeah. Omega is one of the functionals, not a collection.
Okay, okay, one of the functions. I see.
Yes. The composition in here that I mentioned, it is given in my thesis, which, if I remember correctly, is this archive link. Caio, can you check it for me if this is the correct one?
Yeah,
Caio?
just a second. Yeah.
Thank you. Meanwhile, we can define addition on this observable space in the following way. We say that the observable A plus B is the observable such that omega of A plus B equals omega of A plus omega of B for all A and B. This is starting to enlarge our initial notions of observables, because these sorts of observables that we're going to define might not be achievable by an experiment. Although I think that this one still is. You just take two experiments, add up the results, and I think they should leave the averages in the same way, but I might be mistaken something in probability.
So the question is where basically these states, this function of states live in, that you asked me to verify it.
No, I asked you to just check whether this is the archive link for my thesis.
Oh, okay.
Because in my thesis, I'm sure that this is expressed somewhere in terms of expectation values. So you can define addition in this way.
It's on the chat.
Thank you. It is the correct link.
Yeah, it is. I
Okay.
took it from your website.
Oh, perfect. So we can do this. And we already
Sorry,
know.
I did not understand this line that you wrote. So the plus operation was a binary operation on A, right? But why would you need omega to define that operation?
Yes, because I don't have any structure on A yet. So I'm defining the plus operation as being A plus B is the observable such that this holds for, sorry, not for all AB, for all omega.
Oh, okay. Yeah, that makes sense. Yeah.
Yeah, for all AB is up here. For all AB, this holds for all omega. Similarly, I can define how to multiply by scalar. It's actually even more easy, because lambda A is going to be given by f of A, where f of q is just q multiplied by lambda. So in this way, I have now addition and multiplication by scalar. You can check, and this is a good exercise, that A is a vector space. You can also define more things in here. For example, we can define a product, A ball B, to be given by half a plus b squared. I now already know how to take squares by using functions. Minus a squared minus b squared. This is called the Jordan product. However, this is a more natural product for us to define, but it is a bit inconvenient. Instead, it is more convenient to work with another product, which is this underlying dot product that we have. If we were to expand this the square into a product, it would be using this product, and it is more convenient to work with. It leads to a better mathematical structure. This one leads to a Jordan algebra. This one leads to a star algebra. The difference is I can take tensor products of star algebras with no problem. I cannot really take tensor products of Jordan algebras without incurring into some issues. And hence, it is difficult to describe composite quantum systems by using Jordan algebras.
Sorry, another very nice question, but what is the meaning of square of A and B? I thought A by itself, it did not have a structure of containing products, right? So how are you defining A square?
A squared is defined as f of A for f of q equals q squared. Make sense?
But that works as a, so lambda was a scalar, right? Lambda was not a element
Yes,
of A.
we can use here a different function. G of A for G of Q equals Q squared.
So, so every polynomial function is part of the, so if I take any power of the elements of this curly A, they are member of the curly A. Is that what you're saying?
Yes, any function of A is a member of the curly A.
Okay. And the expression within the round brackets A plus B. So how should I understand that A plus B, like in the above sense? Like, so I thought the plus operation was only defined through omegas, and it did not exist at the level of A,
Yes,
the curly A.
I define A plus B in curly A as being whichever observable respects this. And I'm assuming that this, I'm enlarging, if necessary, this curly A to include these guys.
But so usually in functionals, this is just a property of the functional, right? Every functional satisfies this property, right?
Yes, I'm building the algebraic structure in curly A so that at the end of the day, omega is going to be a functional.
Okay, so you're carrying over the property of the functional to the algebraic level, like so the vector space structure level.
Yes, I want this to be a
Okay.
functional, so I'm going to define products and additions in order for this to be a functional.
And just to make sure, so omega of A maps it to a real set. So omega takes operators from A or whatever elements of A, curly A, and maps it to real numbers, is it?
In principle, we start with that, but that's another upgrade we can do. We can now consider that omega of some guy A might be a complex number. In order to ensure that I'm interested only on the real observables, I'm going to define another operation, which is the star operation, which takes from curly A to curly A, and has the following properties. A star equals A, and AB star dot B equals B star dot A star. So this mimics the Hermitian conjugate of a matrix. And hence, I'm going to say that these observables are Hermitian when they satisfy this. In this case, I'm going to have that omega of A is a real number. Let me see. I'm not really sure whether there's an median. I'm not fully sure that this already follows from what I said, but I think it might be a fun exercise to find out. Let me think for a while.
Excuse me.
Yes.
One thing. Is there any benefit to giving such an abstract treatment to the definition of an observable that can be generalized to both the classical and quantum operations we can define in their respective states? Shouldn't be, I don't know, just as powerful to just treat the first term in the equality you first wrote as classical and the second term as quantum, and use their structures as already defined instead of trying to, because I think the causal structure would be exactly the same without trying to generalize both. Is there any
Generalizing both.
benefit to treating it that way?
Generalizing both is in order so we can actually get to the algebraic approach. And the algebraic approach is interesting because it allows us to do quantum field theory in curved spacetime without choosing an observer and without needing to have special symmetries in the spacetime. So at the end of the day, it is a benefit in quantum theory in curved spacetime. And it is one of the most used approaches nowadays. It is particularly mathematical, I admit. So it is a bit inconvenient at start.
But wouldn't, sure, I get it, but wouldn't it be just as powerful to introduce whatever mathematical structure you need ad hoc instead of trying to get it from first principles? Because some things come to mind. If you try to get the result of any experiment as an observable, things that should be obvious in the classical sense, like measuring the height of a box prepared to be 12 centimeters and getting the result 12 centimeters should be immediately realizable in any classical theory. And with the definition of moments that you have, that would be, I think, akin to introducing a delta function in the integral and getting the result 12 from introducing that delta function. So wouldn't it be just as powerful to introduce those assumptions ad hoc when dealing with the classical part of the theory?
When dealing with the classical part, it is easier. But my focus in here is actually that I'm trying to get to the quantum mechanical world. And in trying to get to the quantum mechanical world, I also get a classical description as a consequence. But my focus in here is to go to quantum.
Okay, so the lens you're trying to see this through is quantum, and that's why you try to make it so general, is what I'm getting.
Yes.
All right, okay.
I will end up describing classical mechanics as well, but that is more of an accident than my goal in here. It is just comes as a bonus and allows us to see more clearly what is the difference between quantum and classical. So we have this. And let me check what is next on my notes. So we have found that it seems reasonable to assume that A has the following properties. It is a complex vector space. It has a bilinear product, which is dot product. It has something we call mean evolution. which is star. Let me check if I'm forgetting anything. Oh yes, and it also holds that dot is associative. I'm informing you of this. I don't really think it follows from what I said. So with these four assumptions, we have what we call a star algebra. We can think that the study of physics is pretty much the study of star algebras of interest, and something is interesting in here. If it happens, if this thing is commutative, so a plus b, a times b equals b times a. Oh yes, associative means that a times b times c equals a times b times c. If it is commutative, then it is possible to write a as being the smooth functions from some set x. This can then be thought of as a phase space, and you have that the observables, the classical observables, are simply functions of position and momenta, which is what we have in classical mechanics. If it is not commutative, it is not possible to do so. Hence, quantum theory is characterized by being non-commutative. Our goal, then, for the next lecture is to find I'm not understanding what you're saying. Commutative algebra. Describes the Klein-Gordon equation. Okay.
Nick, does this goal is kind of trying to define a Fock space from this Collier?
Not exactly. A Fock space is another approach that I'm also going to cover in the third lecture, but I don't really need a Fock space to do quantum theory or a Hilbert space.
Okay.
It is interesting, and when you can use one, it is interesting to use it. But to have a Hilbert space in quantum field theory and curved spacetime, you need to have some extra symmetries, which are not always available.
Oh, so that's why a Fock space is not needed on the algebraic approach, because you were
Exactly.
doing everything independent of those symmetries.
Exactly. This approach works in whatever spacetime you pick, as long as it is globally hyperbolic. But to use a Hilbert space, you need to have some extra symmetries to be able to construct the Hilbert space.
Great, great.
Or otherwise, you might have many different Hilbert spaces that are not equivalent, and you need to pick between one of them. And you have no way of choosing. Okay, if there are any more questions, I'll take them now, but I need to leave quite shortly.
Yeah, Radna, what that would, I don't know how to pronounce it exactly, her name, but she opened the mic, and because of the noise, I muted, but I'm not sure if she opened it intentionally or not. So if so, it would be a good time to say what the question was.
Yes.
If Redwood doesn't open her mic, I do have a question.
Mhm.
If you're trying to posit that there is a theory that works under these assumptions, one of those has to be that the quantum field you're using is light, or is it a convenience to introduce that assumption?
One of them has to be that the quantum field is light. Otherwise, it will back react on the background metric, and you start to have to deal with back reaction, which is much more complicated. And there are people who work on this. It is called semi-classical gravity. But I don't know much about it. I never worked with semi-classical gravity before, so I can't really tell much about it.
Right. So in that sense, when you first pose your Cauchy problem, are you expecting to be able to solve linear wave equations in your Cauchy surface given boundary conditions with both a classical and a quantum field?
I assume that I have already solved the Einstein equations with the classical field.
Right.
So that is my background spacetime. I have already solved for the heavy fields, which are classical. And I'm left with only the light quantum fields. So I have to solve the problem for these light quantum fields, because that is going to be necessary in order for me to construct the algebra of observables that I'm going to do on next lecture.
Got it. So from the classical solution, you derive how your quantum objects act, and are you assuming as well that they are light enough that they don't change the metric enough for your original classical solution to not work anymore?
Yes, I am assuming it.
Okay, got it. Thanks.
You're welcome.
There is a question in the chat, if there's time for it. I can read it for you.
Please.
Okay, so when the algebra is commutative, we can see the dot product as a simple multiplication between functions which have real values.
Yes. Exactly.
The person thanked you.
You're welcome. Okay, unless there's something else, I have to leave for another event that is taking place right now. But I thank you very much for your presence, and we can discuss any other questions on at the start of the next lecture. All right, thank you very much, and see you soon. Let me stop recording.